Hello everyone, this is the exam for review for college algebra, and I'm just going to start off with number 1 here, of course. This is a word problem. It's one of the 2 word problems in the actual review. So it says, a rectangular enclosure is built alongside a lake. If the total amount of fencing to be used is 200 feet, what is the largest possible area that can be enclosed? Now, a detail that's not mentioned here is that we're not fencing the side of the enclosure that hits the lake. So that's kind of common with these kinds of problems. Usually you have some type of backing, maybe a side of a shed or something like that, but in this case it's a lake. So imagine the lake is here, and then here we have land where we're building our enclosure. So we're building a rectangular enclosure from these 3 pieces because, again, we're not enclosing the lake side, which again is not in the wording here, but that's something I'm telling you right now. So let's see. So what do we know about the enclosure? Well, we know that we're using a total of 200 feet. So this side plus that side is all equal to 200 feet. So there's a lot of ways you can actually break that down. If you want to call this x, since it's rectangular, this must also be x. And you can call this y. And then, of course, you'll find out that y plus x, which is 2x, is equal to 200. So that means that y is then, of course, 200 minus 2x. So I might as well just write it like that. So instead of writing this as y, I'm just going to call it what it is, 200 minus 2x. And I'll do that. So there we go. Let me erase this. Okay. Perfect. So now what? Well, now we have the side lengths all in terms of one variable, and we're asked to find the largest possible area that can be enclosed. Well, first, again, how to find the largest such area, that's kind of a little difficult, to be quite honest, at this level. But first what we're going to do, I think, is just find the actual area of this enclosure in terms of x. And we can do that, and I'll actually call it a sub x, or a of x, I mean to say. So a for area, so this is a function of x. Area of a rectangle, again, this side doesn't look like it's a straight line, but imagine it is. So the area of this rectangle is going to be x by this amount, by 200 minus 2x. So we have x times the quantity 200 minus 2x. Okay, and if you want to distribute, we can distribute. I'll do that. So we get 200x negative 200x squared. I'll write it in descending order though. So in other words, I'll write the highest power first, negative 2x squared plus 200x. And it doesn't seem like too much is going on here, but since we're asked to find the largest possible area, that means that this function actually has a maximum value. Now, anytime you're asked to find the largest such something or the smallest such something, for problems that are, I guess, to do with algebra, the really only way of doing that is if our function is quadratic, in this case it's quadratic, and if it is quadratic equations have graphs that are parabolas. So if it is an upward parabola, it has a minimum, and if it is a down-facing parabola, it has a maximum. So in this case, it starts with a negative, so the parabola actually faces down. Now, we can actually find out the zeros of this when x is 0, and that'll actually kind of help graph this thing. So if you wanted to graph it like this, then the x values, well, when the area is 0, is either when x is 0 or when this being in parentheses is 0. And of course, it's 200. If 200 minus 2x is 0, that means x must be 100. Notice 2 times 100 is 200, so then 200 minus 200 is indeed 0. So the zeros occur at x equals 0 and at x equals 100. These are the x-intercepts, essentially, which correspond to the zeros of the polynomial function. And halfway in between these zeros, by symmetry, is the number 50, which corresponds to the vertex. Now, I know, since it starts with a negative again, that it's a downward-facing parabola, so the vertex is going to be somewhere above. And we can actually find this value by plugging in 50. Now, plugging in 50 as is like this, it's kind of a little much. But when you plug it in as it's factored above, that's just 50 times 200 minus 2 times 50. Now, 2 times 50 is 100. 200 minus 100 is 100. 50 times 100 is 5,000. That's 5 with 3 zeros. So the parabola will look something like this. Now the actual parabola will go down further, so you'll actually have these kind of extended arrows. So the parabola goes on beyond this. But in the context of this problem, since the y values here represent the area, we don't have a negative area. So in fact, in the context of a sub x, x can only be in between 0 and 100. So it doesn't make sense to draw anything beyond this. So the maximum here occurs, the maximum area value occurs at 5,000 when the x value is 50. Now this is a very geometrical interpretation, and I used a lot of things in the logic here, like in the actual reasoning. But what you can do is just straight up find the vertex, because the vertex will always correspond to the lowest point if it's facing up, or the highest point like we have here if it's facing down. I know it faces down because it has a negative in front. And we know the vertex of a parabola is, I call it V, let's call it h comma k, where h is negative b over 2a, and k is equal to f of h. So of course, if you look at this, negative 2a, that's our a value, 200 is our b value, and then c would be 0 because we have ax squared plus bx plus c. So there is no c, so c is 0. But we don't even need that to find h, so we're good. So if you just plug it in, you get negative 200 over 2 times negative 2. So 2 times negative 2. But notice that's double negative, positive, 200 over 4, because 2 times 2 is 4, ends up being 50. So this is 50. And k is equal to f of 50, f of that h value. Now here I wrote f just kind of by instinct, but it's actually a in this case, because our function is called a, not f. So my mistake there. When you plug 50 in, again you can do it here. Negative 2 times 50 squared plus 200 times 50. And again, you can also use the factored version, but I'm using the unfactored version just to kind of show some difference opposed to how I did it over here and got 5,000. So we should also get 5,000 here, but let's see. So 500 squared is 2,500, so that's negative 2 times 2,500 plus 2 times 5 is 10. There's a total of 3 zeros in addition to that though, so we get 10,000. Now 2 times 25 is 50, so this is going to be 50 with 2 zeros, or negative that, so it's negative 5,000 plus 10,000, which amounts to positive 5,000 indeed. So the largest possible area indeed occurs at 500. Since each of these lengths are in feet, the area unit is going to be feet squared. So the answer here is indeed feet squared. It is the y value of the vertex. When does that happen? It happens when x is equal to 50, which it didn't actually ask that. It only asked for the largest possible area. But if you want to be specific, you can say when x is equal to 50 or when the width is 50. In fact, you can even go further and give the dimensions, that there would be a 50 by 100 because, of course, when x is 50, this is 2 minus 100, which is 100. Okay, so that was enough for this one. Now let's move on to problem number 2 now. Okay, so now for number 2, we're asked to solve the following inequalities and to use interval notation for our answer. Now there's actually quite a few different ways of doing this. Since we actually know how to graph these types of functions, so I'm not talking about the non-zero side, luckily these are both already in that format. So I want to use that method of graphing the non-zero side, and again provided zeros on the other side, which it is like this in both of these cases, and then see when this graph is positive, in other words when it's above the x-axis, and when this one is negative, so when it's below the x-axis. That I think is probably the better way of doing it. And if not, then you basically have to solve the equality, assuming, or maybe not assuming, but replacing the inequality with equality, and then use numbers in between those values as test points to see if this inequality is satisfied or not, and then take the union of those intervals. That sounds confusing. I'll actually show that method first because I think it's a little more intuitive, but then I'll show the graphing method afterwards, which is probably just as intuitive, but provided we know how to graph. So let's take a look. So first, I want to say let's solve the equation. So let's solve x squared minus 144 is equal to 0. So that'll give us x, well, if you factor this, you get x minus 12, x plus 12. So setting each of those equal to 0, we get x is either positive 12 or negative 12. Now there's a few ways of doing that besides what I've done here. Of course, you can add 144 to the other side, square root, you get a plus or minus the square root of 144, which is plus or minus 12, so positive or negative 12. Perfect, just like we have here. Now, these are the solutions to the equation, not the inequality. So what we can do now for the second step is we can pick numbers around these on the number line between negative infinity, negative 12, 12, and infinity. So I want to test numbers in between these and evaluate them, or evaluate the inequality at those values, I should say. So here we can test, let's say, negative 13. 0 is a good one when you have a choice being in between a negative and a positive value, so that's good. And here, positive 13. Now notice when you plug in negative 13 or positive 13, you'll get the same value because its square is still 169, which 169 is bigger than this, so when you subtract, you indeed get a positive number. So these will actually check out. Let me actually write that below. But 0 will not, because 0 squared minus 144 is negative, which is not bigger than 0, so that does not check out. And above, let me write the intervals. So this right here is the interval from negative infinity to negative 12, then from negative 12 to 12, and then finally from 12 to infinity. Now we take the union for this third step of the intervals whose test number checked out. So that's negative infinity to negative 12, union 12 to infinity. Now, what I would do at this step is check to make sure you have the open or closedness of this interval satisfied. But since this is an open inequality, because there's no or equal to, in other words, there are no brackets involved at all. So this is fine. So this is the answer. Okay. And now for this one, the same kind of thing applies, only we also have to check when the denominator is 0 as well as when the entire thing is 0. Now, as it turns out, when the entire thing is 0, a fraction is 0 when the top is 0. So here for step 1, we're not only going to solve the numerator being 0, but also the denominator being 0. So kind of each of these at the same time. So we're solving that, which I'll solve first. That's pretty simple. If you just divide everything by 3, you get x minus 4, and then add 4 to the other side, you get x equals 4. Of course, a really quick way of seeing that is adding 12 and then dividing by 3. 12 divided by 3 is 4. So that's one value. But we also want to solve when the denominator is 0, so let me just say also solve 4x minus x squared is equal to 0. Pulling an x out, we get 4 minus x, and setting each of those factors equal to 0, we get either x is 0 from this factor, or x is positive 4 from this factor. Now, the kind of funny thing here is that we actually have a repeat, and what that really tells me is you have a 0 in the numerator and denominator. So that also tells me that there's a cancellation. In fact, notice if you pull out a 3 and pulled out an x, the 4 minus x and x minus 4 kind of cancel out, and in fact this really reduces to 3 over negative x. But if you don't notice that, it honestly doesn't really change much at all. So I'm not really going to worry about that idea. So instead what I'm going to do is I'm going to proceed in the same way I did with step 2 here, but now with these values, which were solutions to the numerator and denominator being 0. Okay. So again, we have this number line from negative infinity to infinity, and we actually have only 2 values here. One's a repeat. So we have 0, 4, and another 4. So I'm just going to write 0 and 4. And pick numbers around those. So I want to test numbers in between negative infinity and 0, 0 and 4 and infinity. So what do we test? Well, a number less than 0, that's a good number to test, I think, is negative 1. Here we can test 1, and here we can test 5, for example. We're going to plug it into the original inequality and see if it works out. Now, when you plug in negative 1, so I mean, it's a little bit to check like this. If we had noticed that it, if it factoring top and bottom, it simplifies and reduces to 3 over negative x, that would actually help a lot because plug in a negative 1, you get 3 over double negative 1, which is 3, and 3 is not less than 0. So this should not work. And by the way, I should write the intervals above here. Negative infinity to 0, 0 to 4, and 4 to infinity. So that should not work. And similarly, 3 over negative x when x is 1 or 5 is still 3 over a negative number, which is negative. So these should work. Now, I'm going to not write them all out. I'll say one of them just because it's a lot to say by plugging it into the original as is without simplification. So I know it sounds kind of strange because I simplified it and not simplified, and I don't know. But let's plug in negative 1. So 3 times negative 1 is negative 3, minus 12 is negative 15. Okay, let me write that actually. Over 4 times negative 1 is negative 4. I won't write that yet. And then negative 1 squared is positive 1, so it's negative 4 minus 1, that's negative 5. So notice this is indeed positive 3, which is not less than or equal to 0. So this does not satisfy the inequality. And again, you can check very similarly that 1 and 5 will actually satisfy the inequality. So step 3 here is now to take the union of the ones that checked out. Now, the reason why we can't include 4 is because before simplification, this is kind of a subtle thing, but even if you were to simplify, as is, x cannot be 4. Once you simplify 3 over negative x, x could be 4, but as is, x cannot be 4. So technically 4 is not a solution to this inequality. So that's why it's important to actually leave it in there instead of simplifying and forgetting about it. So it's really best to not simplify these for some reason. It kind of works out nicely. So what we end up getting here is 0 to 4 union 4 to infinity. Now, because this is an or equal to scenario, I want to check the endpoints. Now, 0 can certainly not be plugged in because you'll get a 0 denominator. In fact, that came from the denominator being 0. And in fact, to think about it, anything that came from the denominator being 0 should automatically be open because you couldn't plug it in anyways, you would get a 0 denominator. So the only thing that could possibly be closed, bracketed, if, again, this is a closed inequality, an or equal to scenario, or if they came from the numerator being 0. But since when the numerator is 0 also matches a 0 in the denominator, then we actually have a pure open interval here, or a pure union of open intervals. Okay, now I said I wanted to do this also by graphing, so I'm going to erase and redo it, and we'll see how much shorter it is. Right, so that solution, again, wasn't bad, but I think graphing will be a little shorter and more intuitive, provided we know how to graph. Now again, since 0 is on the other side, I'm going to graph this function. So I'm going to call this f of x, and similarly I'll call this f of x, but I'm going to do the a first before I do b. I'm just kind of mentioning that we're graphing these functions on the non-zero side of the inequality. Okay. So if we graph this this polynomial f of x is equal to x squared minus 144, well, I know the zeros of this are when x is equal to positive or negative 12. It's pretty easy to see when that's 0, add 144 to the other side, square root. I kind of mentioned that in the previous way of seeing it. So that shouldn't be too hard to see. So we have a parabola that passes through negative 12 and 12. And more importantly, it's a facing upward parabola. Now where it actually intercepts the y-axis is not important, but when x is 0, you can clearly see it's negative 144. So this is not to scale, but the parabola will look something like this. But again, where it crosses the y-axis technically as a negative 144, so clearly this is not to scale, because to scale that would be like way down there or something like that. But what is important here is we want f of x to be bigger than 0, and f of x are the y values of points on this parabola. So I want the y values to be above the x-axis. Now that happens when the graph is above the x-axis. So notice it crosses through the x-axis at these 2 points, so we're going to check the shadows of the graph basically on the x-axis. Here, it's above the x-axis, here it's below the x-axis, and here the function is above the x-axis. Since we want to be positive, which is above the x-axis, then we take the union of the intervals that correspond to when the graph is above the x-axis. So that's negative infinity to negative 12 here, and 12 to infinity. Since it's strictly bigger than 0, we don't want to equal 12 or negative 12. So there we go, we get our answer, which is the exact same answer we had the previous way, of course. And it's very funny because we actually see the same number line we drew, but now we see it with the graph that helps us view why these intervals are chosen, basically. And in fact, test numbers would just be any one of these that correspond to a positive value. The test number here would correspond to a negative value, which doesn't satisfy this, and you kind of keep going like that. Great. So again, it's very similar, okay? But to graph a rational function, we want to simplify. So here I'm going to have no choice but to simplify. So f of x is going to be factor the top, pull out a 3. Factor the bottom, pull out that x. Okay, so now remember, x minus 4 and 4 minus x are so close to being the same. All we need to do is pull a negative out, and they will be the same. So pull a negative out from the bottom one, that'll swap the difference and make it x minus 4. And if you don't believe me, well, distribute the negative and you'll get negative x plus 4, which is the same as 4 minus x. Now these cancel and we get that 3 over negative x I was talking about. Now the only real issue here, and I'm going to write it actually as a negative 3 over x if that's okay with you. Of course it should be okay with you. Now the only issue is that since we canceled x minus 4, then that tells me that x cannot be 4 in the original thing, because you'd have 0 over 0, which is technically undefined. So I'm going to put a restriction here that x cannot be equal to 4. In fact, as a graph, like graphing-wise, that corresponds to a hole in the graph of the function. So let's see that here. Now, if you don't know, the graph of 1 over x looks something like this. And the graph of 3 over x will look very similar, just stretched out by a factor of 3. But negative that is actually flipping it across the x-axis. So these are just transformations that I'm really talking about here. But in fact, really what you can notice is that since we have a 0 in the denominator when x is 0, that means we have a vertical asymptote at x equals 0. So in fact, maybe I'll write over here above, I guess I can write over here. We have a vertical asymptote, which I call VA, at x equals 0, and since the degree of the top is less than the degree of the bottom, then we have a horizontal asymptote at y equals 0, which actually isn't very necessary for solving this inequality by graphing, but still it's something I want to mention. Now when I say degree, I'm talking about the highest power of x. Highest power of x on top is technically 0, highest power of x on the bottom is technically 1. Okay, so we can definitely see this kind of image here, something like that. Now, if you want to actually see where what is, then you can just plug in values. So for example, when x is bigger than 0, this is going to be 3 over, well, so let's imagine x is positive 1. So this is 3 over 1, but it's a negative, so it's going to be a negative value. So what we end up getting is this image. Again, because there is a 3 on top, that means it's scaled out by a factor of 3, or I guess stretched out vertically by a factor of 3, which I don't really want to worry about too much because that's being specific into graphing. I just really care about when this is above or below the x-axis. In fact, I want this to be below the x-axis. And where is it below the x-axis? Well, here it's above the x-axis, and here it's below the x-axis. Oh, also we said there was a hole at 4. So technically at x equals 4, let's say this is x equals 4, there's actually a hole on the graph. So where it's below the x-axis is actually in this interval, which is from 0 to infinity, but since we can't plug in 4, we have to break this up as the interval from 0 to 4 union the interval from 4 to infinity. And in fact, that's the answer. And that's the same answer we got before, so there we go. Let me just write it here in black. 0 to 4 union 4 to infinity. Perfect. So yeah, much shorter than the previous method, but again, we have to understand and know how to graph. That'll definitely help with this method in mind. So now moving on to number 3. Okay, so for number 3 here, we want to find the polynomial function with zeros, negative 1, 1, and 3, and also satisfying that it passes through this point, 1, 36, or negative 1, 36. Now, any polynomial function will actually have factors corresponding to x minus its zeros. So let me just say that if x equal a is a 0, then x minus a is a factor. It's a very well-known fact with polynomials, and in fact it's an if and only if statement, which makes sense because if you have a factor of x minus a, when x is 0, the whole thing blows up to 0. Because it's a factor, so that means it factors as a bunch of things multiplied. When x is a, it's 0 times a bunch of other things, which is just 0. So that's kind of nice. Now, these are said to be the only zeros here, so that means we have x minus each of these as factors. And we also may have a constant factor, so in fact what we can say now is that our polynomial function, let's call it f of x, must be of the form some number. I probably shouldn't have used a here. Let me just use r. I hope that's okay, just so I don't seem too confusing, because here I want to use a because a is usually used for leading coefficient. So I probably should have been more careful there, but that's fine. Times all of the factors that we get from these zeros. So this is x minus negative 1, x minus 1, and x minus 3. Perfect. Now if we want, we can actually simplify this a bit. This is of course x plus 1, that's a difference of squares, and we can distribute and so on. But actually it's best to keep things factored, I think, because maybe we can solve for a better. Because we still don't know what a is, and we used this bit of information, but we did not use this bit of information. So remember that this bit of information here tells us that this is a point on the graph of this function. So when x is equal to this x value, then that means this y value will be our f of x value. So we can actually say when x is equal to negative 1, yeah, there's a huge typo there, isn't there? Right, so I hope we see the issue. When x is negative 1, well, negative 1 is a 0. So I'm probably going to have to fix that. Let's make it 2 or something like that. Let's see if it works out when x is 2. And I'll just fix the document. So when x is 2, we get f of 2. So I'm replacing all x's with 2. This is x plus 1, so it's going to be 2 plus 1. This is 2 minus 1. And this is 2 minus 3. So altogether, f of 2 is 36. A is going to be multiplied by 2 plus 1 is 3, 2 minus 1 is 1, and 2 minus 3 is negative 1. So, okay, so this is negative 3a. So altogether we have 36 is equal to negative 3a. So that means dividing by negative 3, a is equal to negative 12. Perfect. So now plugging that back in, we have f of x is negative 12 times x plus 1, x minus 1, x minus 3. Now this is actually acceptable, but just because we can, I'm going to FOIL this out a bit. In fact, I'm going to FOIL it all the way. So x plus 1, x minus 1, that's a difference of squares. So I'm going to get x squared minus 1. And then actually FOILing this out, x squared times x is x cubed, x squared times negative 3 is negative 3x squared, negative 1 times x is negative x, negative 1 times 3 is positive 3. Then of course the negative 12 that we shouldn't have forgotten about. Distributing that, we get negative 12x cubed plus 36x squared plus 12x minus 36. So this is actually an f of x function, fully expanded out and all that. So pardon that small typo there, but I'll change the document so you won't even see that issue. Good. So now moving on to number 4. Okay, so for number 4 here, we're asked to find all asymptotes, vertical, horizontal, and possibly oblique asymptotes, if there are any, and the domain of this function. Now, the first thing I'm going to notice is that we can possibly simplify this, so I want to. But remember that if something cancels out, when that canceled factor is equal to 0, that's excluded from the domain still, because as is, we can plug in that value and get 0 over 0. So we'll actually see that, I think here, I could be wrong, but let's check it out. So the top definitely factors, the two numbers that multiply to negative 15 and add to negative 2 are 5 and 3. Specifically, it's positive 3 and negative 5 to make that work. So that means this is going to factor as x plus 3 times x minus 5. The denominator, I'm going to actually pull off to the side here. Factor out of 3, you get x squared minus 9. We're going to have 3 on the outside, but x squared minus 9, of course, is a difference of squares. That's x plus 3 times x minus 3. And of course, where I'm getting this 3 from is because this is the square root of this 9. Okay? And we indeed see cancellation of the x plus 3's, but this tells us that x cannot be equal to negative 3. Okay? Because if x was negative 3 before cancellation, you get 0 over 0. So plug in a negative 3 to the function as is before simplification will give you undefined. So negative 3 is excluded from the domain. So we'll actually see that when we find the domain. This, by the way, corresponds to a whole, like we saw in one of the previous problems, number 2, I think. So this will not have to do with vertical or horizontal asymptotes, but it's still something to kind of keep in mind, but mainly it has to do with the domain. Okay, so now this function heavily reduced, well, I guess reduced a bit actually, but looks kind of heavy, I guess. We end up getting this. Now, when the top is 0, that just corresponds to a 0. So it corresponds to an x-intercept, basically. So when x is 5, you can say that that's an x-intercept of the function, but that's not really worrisome to me because I want to find the asymptotes. Now, there are 2 types of asymptotes mainly that we find, vertical and horizontal. We kind of mentioned that in problem 2. So vertical asymptote, which I label as VA, is when you have any denominator be equal to 0, basically. So set all your denominators equal to 0, or denominator factor equal to 0. Let's just say set denominator equal to 0. And that actually happens when x is equal to 3. Now, the only real issue is that we have to do this after cancellation, which we have done here, so that's good. Otherwise, we would get mistakenly that x equals negative 3 is a vertical asymptote, when in reality it's just a whole. So something to keep in mind. So when x minus 3 is equal to 0, again, I'm just setting the denominator equal to 0. But that corresponds to setting each of these equal to 0. But since 3 is never 0, we ignore that. So we're really just setting x minus 3 equals 0. So that's why I said that. And when x minus 3 is 0, that means x is equal to positive 3. And you can see that pretty simply by just adding 3 to the other side, and you end up getting that. So this is actually our vertical asymptote, which I'll actually summarize in a moment. Now for horizontal asymptotes, there are basically 2 cases. And if you want to think about it as 3 cases where the third case is an oblique asymptote, then you can. But it all has to do with degree. The degree of the numerator, the degree of the denominator. What is the degree? Degree is the highest power in the numerator and denominator. So here, the highest power of x is 2, highest power of x is 2. So the degree in the numerator and denominator are both the same. They're both 2. Okay? Here, the degrees are 1. Distributing that 3 doesn't affect the degree, right? You just get 3x minus 9. So that's the degree is still 1. The highest power is 1. Now, if there was no x here and it was negative 5, I call that degree 0 because there's no x. So the highest power of x technically is 0. Just so we kind of know my lingo. Okay? So case 1, what I call case 1 anyways, is when the degree of the numerator is less than degree of the denominator. And in this case, the horizontal asymptote is just simply put y equals 0. And that actually doesn't happen in this case. So I'm just kind of, I guess, lecturing on top of this just to remind us how these things work. Now, the second case, though, is when the degrees are the same, which actually happens here. So here the degrees are equal. So the degree of numerator is equal to the degree of the denominator. And what you end up getting here is the horizontal asymptote is y is equal to the leading coefficient of the numerator, I'll write that as LC of numerator, over LC of denominator. So what is LC? Well, I said it real quickly, but LC stands for leading coefficient. Leading coefficient or lead coefficient is the number in front of the largest power. It's the coefficient of your highest power term. So here on top, this is going to be 1x, and here in the denominator, after distributing, you'll have a 3x. So, in fact, here in this case, we do have case 2, not case 1. We do have case 2 indeed. And for our particular case, we end up getting y is equal to 1 over 3. So this is our horizontal asymptote. Perfect. Now, what about the domain? Well, for the domain, I'll kind of actually bring that over here. We could have actually found that earlier before getting into asymptotes, but it's fine. X cannot be negative 3 from our whole, And it also cannot be positive 3 because we have a vertical asymptote there, but again, we got that by setting the denominator equal to 0, and the denominator can't ever be 0 anyways. And in fact, the way you always find the domain is before cancellation, just set denominator is equal to 0. And when you set this equal to 0, you'll end up getting x equals positive 3 and negative 3 anyways. Good. So the domain is the set of all x values such that x cannot be equal to 3 or negative 3. This is in set builder notation. If we like interval notation, then this is negative infinity to negative 3, union negative 3 to 3, union 3 to infinity. But I didn't specify which notation to use. I'll box this one. And I should also box our answers here for vertical and horizontal asymptotes. So let me say our vertical asymptote is x equals 3, and our horizontal asymptote is y equals 1/3. So there we go. Those are our answers here, asymptotes and our domain. Now I didn't mention that third case, which is oblique asymptotes, but that's very specific. That only happens when the degree of the numerator is 1 more than the degree of the denominator, and the oblique asymptote is basically just the quotient you get when you do long division, polynomial long division. And that'll correspond to a linear function, which is a line that is not vertical or horizontal, so it's some line like this, for example, and that's what an oblique asymptote is. So instead of having a horizontal one, you have like a slanted one. So oblique asymptotes are sometimes referred to as slant asymptotes. But I don't believe that'll actually make it on the exam. I think stressing these scenarios of horizontal asymptotes is actually more important, for me anyways. So now moving on to number 5. Alright, so for this problem we're asked to factor this over the complex numbers, so we may actually see I making an appearance here possibly. So what I want to first use is the rational zeros theorem, and in fact I kind of actually give a hint as well in the review that says use rational zeros theorem along with quadratic formula possibly, and I even mentioned synthetic division, and we'll actually see that right now. So recall rational zeros theorem says that you have a rational zero of a polynomial of the form factor of the constant divided by factor of the leading coefficient. So the leading coefficient here is 1, and the constant term is negative 15. So we're going to look at factors of 15 and factors of 1. And the rational zeros theorem specifically says that we have plus or minus these, because technically, since this last number is negative 15, even if it was positive 15, technically 15 is negative 3 times negative 5. In other words, negative numbers are considered for factors. So just writing plus or minus helps. So I'm writing factors of these, which are 1, 3, 5, and 15 itself, and factors of 1, which is just 1. So all of these divided by all of these. So it's 1, 3, 5, 15, all over 1. Now the fact that it's all over 1 means that they're just the top numbers alone, right? Anything divided by 1 is itself, so we just end up with the numbers 1, 3, 5, and 15, but with plus or minuses. So we have a total of 8 different themes. Positive or negative 1, positive or negative 3, positive or negative 5, and finally positive or negative 15. So the ones that work, if any, will satisfy this being 0. So honestly, you can just plug any of these 8 in and see which ones give you 0, and then just select those as being your roots. So you have your 0 basically. And if you want to factor it, then we know x minus that 0 is a factor, and we discussed that earlier actually. But instead of plugging it in directly as is, synthetic division is actually a much quicker way of doing this. And I'm going to change things up as I go along, and I'm just going to go in order. So I have no idea, where it is. It could be early on or it could be later on. So I don't know. So what I'm going to do to set up synthetic division is I'm going to pick a box number. The box number is going to be one of the possible zeros. And then to the right of this box number, I'm going to write the coefficients of our polynomial. 1, negative 5, 11, and negative 15. The rules of synthetic division are to bring the first number down for free, multiply by the box number to get the next diagonal number here, add straight down to get this next number, and then repeat the process. And the last number will be our remainder. And the remainder of this division actually, is the value when you plug it in. So for example, we'll see when you plug in 1 right now. whatever this number is will actually correspond to the value you get when you plug in 1 the old-fashioned way. And in fact, I'll just check. When you plug in 1, you get, well, all powers of x are just 1, because 1 to any power is 1. So it's 1 minus 5 is negative 4. Negative 4 plus 11 is going to be, 7, and then 7 minus 15 is negative 8. So it's not 0, but let's just see that this works. So I said it was a negative 8, is that right? Well, let's see. So let's see. So we multiply this by the box number, we get 1, add straight down, multiply by the box number, add straight down, multiply by the box number, add straight down. Good, so it seems to work. We get the same value we got when we plugged it in the old-fashioned way. But as we'll see soon enough, this is actually quicker in the long run. If you plug in something like 3, cubing it and squaring it, that takes a while. This process, even though it looks kind of slower, is actually quicker in the end. Okay, so I'm actually going to not use a 1, and now we're going to check negative 1. So this process could possibly take some time. So not 1, but now negative 1. Bring this down, multiply by the box number, add straight down, multiply by the box number, add straight down, multiply by the box number, add straight down. So clearly this is not 0 as well. So 1 and negative 1 didn't actually work. Let me just double check to make sure we're doing okay. Okay, it looks fine. So negative 1 didn't work. Let's try 3. Okay, let me erase this work here. So 1 times the box number is 3. Add straight down, you get negative 2. Multiply by the box number, we get negative 6. Add straight down, we get 5. Ooh, look at that. 5 times 3 is 15. If you add these, you indeed get 0. Perfect, it worked. So that means positive 3 is a 0. And because this is actually a division setup, really what this says is the remainder is 0, and the quotient is actually the polynomial whose coefficients are these. So the coefficients here are 1, negative 2, and 5. And the polynomial that this corresponds to then is 1x squared minus 2x plus 5. So in fact, what we have shown so far is that this polynomial factors as this times x minus our 0 we just found. Perfect. Now, I'm not going to do it, but FOIL it out, you'll get that. Okay? Pretty amazing. Now, can we factor this? There are methods to actually factor without using quadratic formula, but they require completing the square. It gets a little messy. It's not too bad, honestly. It's just a little messy. So instead of doing that, I'm just going to actually set this equal to 0 to find the zeros, and then remember that x minus the zeros are factors. So setting this equal to 0, there are actually no two numbers that multiply to 5 and add to negative 2. No integers that make that happen. So that means we're going to have to use quadratic formula to solve this non-factoring. So let's recall quadratic formula. X would be equal to negative b, I'll write it off to the side here. If ax squared plus bx plus c is equal to 0, then that implies, this is quadratic formula, that x is equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. Perfect. So now when a is 1, b is negative 2, and c is 5, so we can clearly see the coefficients here, plugging them into the quadratic formula gives me double negative 2 plus or minus the square root of negative 2 squared minus 4 times a times c, so that's 1 and 5, all divided by 2 times a, which is 2 times 1. So this simplifies a lot. Double negative 2 is positive 2, plus or minus the square root of, this inside of the radical, negative 2 squared is 4, and 4 times 1 times 5 is 20, so it's negative 20. So this is 4 minus 20, which is negative 16. Now the square root of a negative number is not a real number, but we can write it as an imaginary number by getting rid of the negative for an I on the outside. In fact, another way of thinking of it is that since the square root of 16 is 4, the square root of negative 16 is 4i. So in fact, this is thought to be 2 plus or minus 4i all over 2. And there's a lot of ways you can actually cancel from here. You don't just cancel the 2's, okay? You can either pull out a 2 from the top, which I'm going to actually do that way. So we get 1 plus or minus 2i as a quantity all over 2. The 2's cancel and you get 1 plus or minus 2i. That's the way I like to do it. There's another way of doing it though, where you split the fraction up as 2 over 2 plus or minus 4i over 2, which of course reduces to 1 plus or minus 2i. So you still get these. So these are our x values, our zeros. So that means that our factors are x minus these. So there's two values here. It's x equals 1 plus 2i and 1 minus 2i. So x minus 3 is still hanging out there. And now we have shown that this actually factors as x minus each of these. So x minus 1 plus 2i. I'm going to skip a step here. I'll kind of explain what I'm doing though. And x minus 1 minus 2i. So we have now successfully factored this polynomial over the complex numbers. Now, just to explain what I did there, is I actually wrote x minus each of these one at a time. So if I had x minus 1 plus 2i, the negative distributes and you get x minus 1 minus 2i. If you have x minus its conjugate, 1 minus 2i, which is the other one here, right, this is plus or minus, so there's these two. Distributing the negative here gives us x minus 1 plus 2i. So that's how I got those. Okay. So great. So we factored this as linear factors over complex numbers. Fantastic. That was number 5. Now we can move on to number 6. Okay, so for problem 6 here, we're asked to solve for each of these for x in each of these equations. And it seems like a lot, but these are actually not that complicated. But notice there's kind of been a split in the review. 1 through 5 were polynomial, rational expression type of equation, or type of questions, really. And 6 and on are like exponential, logarithmic type of questions. So it's really to our benefit to understand what logarithm means and know the difference between a logarithmic form and exponential form. And we'll translate between them very often. So in fact, this logarithmic form we're going to actually convert to exponential form in an attempt to solve for this, to solve for x. So, and then that's because x is only in one location here, so there's no simplifying needed here. You actually kind of can simplify this using some logarithmic properties. I'm not going to get too crazy though, I'm just going to convert it to exponential and see what happens. So the base is 3x, so that means the base in exponential is also 3x. The power is what the logarithm solves for. So this is what I consider the power or the exponent. I mean, that's what it is in exponential. But when I say when I consider that, I usually use the phrase logarithms solve for powers. Because the answer to the logarithm is what this base to that power is. So this base to that power will give you the inside. So that helps us translate. So we get this base to this power is equal to the inside. In fact, very often people kind of think of it like this, that imagine this gets brought down, like shifted a little bit so that 3x is down here now, and then swap 3 and 27 and get that. So that's a nice visualization, but I think it's easier to remember that this is the base, log solve for power, so that's the power, and then the inside is the result of that. Okay, and now we can actually use some properties here and cube this, and we end up getting 3 cubed times x cubed is equal to 27 by distributing this power to each of these parts of the product. 3 cubed is of course 27, so we get 27x cubed is equal to 27, but of course if you divide both sides by 27 you get x cubed is equal to 1, they both cancel out. And then taking the cube root of both sides we get x is also equal to 1. And in fact what's really interesting here, just because the problem we just did before this problem, number 5, had to do with complex, basically complex solutions. X cubed equals 1 if you solved for 0, if you write it so that it's equal to 0. X cubed minus 1, the polynomial x cubed minus 1, actually factors as x minus 1, and notice this 0 is x equals 1, times x squared plus x plus 1. And x squared plus x plus 1 is 0 for complex values. So there are actually also complex solutions to this, but I'm just going to assume that x is not complex. And in fact, the base is never complex. You can kind of talk about complex bases, but that's getting way beyond what we want to talk about. So there we go, that was A. Now for this one, there is a way you can solve this by converting this exponential to logarithmic form, But I think that's a little too crazy. In fact, all we really need to do here is find a common base and then apply this one-to-one property of, well, of exponentials. And the one-to-one property basically says that if you have b to the x equals b to the y, and the bases are both the same, of course, they're both the same b, that are positive and not equal to 1, then x must be equal to y. Now, the not equal to 1 part makes sense because 1 to the 3 is equal to 1 to the 4, for example, but 3 is clearly not 4. So when the base is any non-negative or positive non-1 number, then this property is true. So this is known as the one-to-one property. So I'll just write 1-1 for one-to-one. So I want to get things in the same base. So I'm going to notice that 16 is actually 4 to the second. We have 4 here. And you could actually kind of get this as 4, but you'd have to divide by 2. It gets kind of weird because this is technically 2 to the 2x times 2. Right? You can write this as 2 to the 2x times 2, and 2 to the 2x is technically 2 to the 2 to the x times 2. So you can write this as 2 times 4 to the x. So there is a way to get it as a base 4, but what's actually better is that 16 not only is 4 to the second, 16 is also 2 to the 4th. And in fact, I'm going to notice here, since 4 is 2 to the 2, I want to get them in the smallest base we can. And the smallest base possible here is 2. That actually is the best thing to do. So I'm going to replace 4 with 2 to the second. This 2 stays the same, so that's fine. And I'm going to write 16 as 2 to the 4th. Recognizing that 16 is 4 squared, but 4 is 2 squared, so 2 squared squared is 2 to the 4th. Perfect. A little bit of work to do, but then we're almost there to use a one-to-one property. So if we multiply these two powers, we get 2 to the 2x. So 2 to the 2x times 2 to the 2x plus 1 is equal to 2 to the 4. Then we can combine these by adding the exponents. Notice 2x plus 2x is 4x plus 1 equals 2 to the 4. Perfect. Now we can definitely apply the one-to-one property, and we're almost done. So the one-to-one property says that if the bases are the same in this equality, which they are both 2 in this case, then the exponents must be the same. So let me just write 1-1 here, saying that I'm using the one-to-one property, and I'll actually bring it up here. We get the exponents must be the same. So that's 4x plus 1 is equal to 4. Okay, subtract 1 from each side. These cancel. 4x is equal to 4 minus 1, which is 3. Divide by 4. These cancel. X is 3/4. Perfect. Now something I did not do in the previous problem is actually check it. And this one's actually kind of weird to check. It's not difficult because 2 times 3/4 is 3 over 2, which is 3 halves, plus 1 is 5 halves. So that's 2 to the 5 halves, but then 4 to the 3/4. So it kind of sounds weird, but if you write them both as powers of base 2, the powers end up combining into 4, and 2 to the 4th is 16. So you can try that on your own and check that. This one, when x is 1, log base 3 of 27 is indeed 3, because log base 3 of 27 means we're looking for a power that when you raise 3 to that power, you get 27. And since 3 to the 3 is 27, then log base 3 of 27 is indeed equal to 3. So when x equals 1, this definitely works. So that's nice. Now this one is actually very, very interesting. I think it's actually super simple. First, I'm going to get e to the 5x by itself by multiplying both sides by the reciprocal of 4/3, which is 3/4. A lot of cross cancellation here. Notice 4 goes into 12 3 times, so 4 goes into 120 30 times. 3 times 30 is 90, so we end up getting these cancel out completely. E to the 5x is equal to 90. Great. And now to undo e, this is an exponential form. I'm going to convert this into logarithmic form, which we actually could have kind of used here, but common base, when that can be used, I think is probably a better thing you want to kind of keep practice of. We probably should border these things so we don't get confused. If you get a little confused, it's okay. All right, so this is an exponential form. We have a base, we have a power, and we have the result. So remember, for logarithms, the base is the same, and log solve for the power. So I can write this as log base, the base is e, of something equals something, but since log solve for powers, the 5x power must be what the logarithm is equal to. Okay? Making the inside being the result of this exponential, which is 90. And again, you can think of it as bringing this down and swapping those, and you get log base e of 90 is equal to 5x. That's another way of seeing that. And now we're almost there. All we need to do is divide by 5 to get x, but I'm going to kind of pull a fast one on us. Log base e is actually known as natural log of whatever the same inside is. So log base e of 90 is natural log of 90, and natural log has the abbreviation ln. So that's the function ln. So now multiplying both sides by 1/5, dividing by 5 basically, we get x is equal to 1/5 ln of 90. And that's how I'm going to leave my answer. Now I should probably mention sometimes parentheses are written, sometimes they're kind of not. ln 90 means ln of 90, and similarly here, the way the review has it is there's no parentheses, it's just log base 3x 27. So that means log base 3x of 27. So I'm just kind of showing those sometimes. Okay, so now moving on to number 7. Okay, so number 7 here has 3 way different types of problems. In fact, the instruction for 7 is just answer the following. So for A, we're asked to find the exact value of this. For B, we're asked to combine this somehow into one single logarithm. And for C, we're asked to approximate this. And it says we can use a calculator as well, but a lot of calculators don't actually have a function for log of any base. In fact, they only usually have log, which is log base 10, and ln, which we know is log base e. So we'll get to that, but I'm just going to go in order, of course. Now, what I want to do here is I want to use this property of logarithms that if you have a base to log base, that same base of something, those cancel out and you just get this. In fact, it's also true, we won't need it here, but it's also true that log base b of b to the x would cancel out and just give you x. So I want to use that here. The only problem is this is e to the log base e cubed of 64, not log base e. So maybe there's a way for us to rewrite it like that. Another possibility is we can actually convert this expression, call it x or something like that, and convert it into logarithmic form because technically it's an exponential form. So that's something we can do as well. In fact, I'm thinking that's probably the better approach. It's kind of more systematic way of taking care of this. It's an exponential form, so let's let it be equal to x, and then we convert it to logarithmic form. So the base is e here, because the base of this exponential is e. So we get log base e of the result of the exponential, which is x equals the power of that base, which is log base e cubed of 64. Okay, so it doesn't really seem like we've done much actually. And in fact, at this point, it's kind of difficult to maybe continue. It's hard to tell what you should do. I guess we can, well, think of it like this. This is in logarithmic form from this side and also from this side. So we can actually convert this back into logarithmic form, or back into exponential form, I should say, but using this base instead of this base. Of course, if we went to this base, if we use this base, we get back the original expression. But using this base, we get something else. We get e to the 3, that base, raised to the power. Remember, log solve for power, so what this log is equal to is the power of this. So log base e of x, we just call ln of x. So ln of x. So let's see, that base to that power is equal to the inside 64. Let's try ln of x, good. Great, now this actually has a lot of potential. In fact, I know exactly what to do here. Because what we can do now is we can actually use an exponent property to write this as e to the 3 ln of x equals 64. And then now, if you wanted to, you could actually convert this back into logarithmic form and say that, ln of 64 is equal to 3 ln of x, and then you can divide by 3 and then take e to both sides. So there's a lot of converting back and forth between exponential and logarithmic form. So it's a little exhausting in that sense. But there's actually a better way of doing it, I think. and that is to do this. We can actually use the fact that if you have any log, no matter what the base is, of x to a power, the power comes out. So in fact, I'm going to use this property in reverse to bring the coefficient of this log in as a power. So I'm going to write this as e to the ln of x cubed, and that's equal to 64. And now I'm going to use the fact that ln means log base e, and e to the log base e of something cancels out like we saw before. So we see that here, and we just get x cubed is equal to 64, and I didn't need parentheses there. So x cubed is 64. Let me use that. I'll write that here. So now we get x cubed is equal to 64. So we can cube root both sides. Of course, we know this is 4 cubed. So if x is equal to 4 cubed, then cube rooting both sides means that x is equal to 4. Remember that when you cube root, you don't get a plus or minus because it's an odd power. So there we go. We get x is equal to 4, and now we can move on to part B. And here we're combining this to one single logarithm. And I want to use some properties, like I said. And the big properties we're going to use here are that, again, if you have, maybe I should write them off to the side here. And I'll write them with ln. Even though they're true for log of any base, I'm just going to write them with ln, okay? So the first property is that if you have r times ln of x, this is the same as ln of x to the r. We just actually used that right now. And then if you actually have ln of x plus ln of y, this is equal to ln of x times y. Let me move this over a bit. Okay, and then also if you have ln of x minus ln of y, very similarly, this is division on the inside, ln of x over y. Great. So I want to use that here. So notice the only coefficient is this 5, so I'm going to bring that in as a power first. So we have 5 ln of x minus 2 all to the 5th plus ln of 2x minus ln of 3x minus 3. And I'm just going to go one at a time. So first, that 5 shouldn't be there, so the 5 came in as a power. So, excuse me. So first I'm going to go from left to right and just add those. So I know adding two logs is taking log of the product of the insides. So this right away is going to be ln of the product. So it's x minus 2 to the 5th times 2x minus ln of 3x minus 3. And I also know that subtraction of logarithms is the log of the quotient. So we're dividing here. So that means this combines as ln of the first one. I'm going to rearrange it if that's okay with you. Over the second inside, 3x minus 3. And that is the answer for part B. Fantastic. And now this one for approximating, there's a lot of ways of doing this, but to do this with the change of base formula, which is something maybe I should mention here. I'll write it here actually. So I'll write COB for change of base. And it basically says log base, any base of x, is equal to log base some other base of x over log of that same base of the original base. So it sounds weird at first, you're changing bases from B to C, but this is nice because our calculators again only know log base 10 and log base E. So, for example, if we set C to be equal to 10, then this says log base 10, which is just log of x over log of B. Also, if we take C to be E, then this is log base E, which is ln of x over ln of B. Perfect. So here, where B is 4 and x is 20, I'll actually use this one. Doesn't matter which one you use. If you want to use this one to check or this one to check, it's best to verify they're both the same. They both give the same value. But I'm actually going to use this fact to write this as ln of 20 over ln of 4. Type that into my calculator and approximate, and I get about 2.1609. I'll round it to 3 decimal places and write that as 2161. Now I didn't specify what to approximate it to. On the exam it will probably specify, but if it doesn't specify, then just kind of use your best judgment and I can follow the work anyways. Right, so before moving on, I looked back at this and I kind of realized something. So for A, I wrote x equals 4, but x was something we came up with. So the actual answer is not x equals 4, but just 4. So what we're saying is that this expression is equal to 4. And you can verify that with the calculator, provided you type it incorrectly, of course. Notice that for the exponent, you may need to use change of base. And in fact, that's another way of doing it, to rewrite the exponent using change of base and then taking e to that. You'll kind of notice some things. So it's a different way of doing a. A is kind of strange because it can actually be done in a few different ways. But I just wanted to say that here. And now we can move on to number 8. All right, so for this problem, we're asked to find out how much these two people will have after 20 years and basically who will have more. So I'll just read it. It says, Bill invests $25,000 at 10.26% compounded monthly. Desmond invests the same amount, $25,000, as Bill, so the same amount as Bill, but compounding continuously at a different rate of 9.5%. So who has more after 20 years? And then by how much? So the by how much part actually ensures that we do the work and don't just guess. Now, of course, even then it's still hard to guess because you may think, okay, well, Bill his interest amount is more, so he may pay more actually, but he's being compounded less frequently than Desmond is. So it's actually kind of balanced in some sense. It's hard to tell. But just looking at it, the bigger rate usually determines, even though the compounding amount is different, obviously, compounding amount of times compounded per year is different. That's fine. But the interest rate, I think, usually overtakes. But let's see, I could be wrong. So I'm going to break this up into two different situations. Bill and Desmond. All right, so let's calculate their amounts. And what we're going to do is we're actually going to use compound interest formulas. Now there's two of them, okay? There's compound interest and continuous compound interest. Obviously the continuous formula we'll use for Desmond. Don't remember what that is? That is A equals P times e to the RT. Sometimes people remember this as A pert, just because it looks like it spells that. A is the amount after, P is a principal, starting amount, E is the number we know and love, and R is the rate, but in decimal. And then T is the amount of years that pass, which is 20. So we know all of these things. Let me write them down. P is the initial amount of 25,000. Okay. R is our rate in decimal, which is 0.095. Okay. And T is the amount of years that pass, which is 20 years. Okay. Now Bill's formula is a little different. This is a non-continuous compound interest. And this is A is equal to P times 1 plus R over N to the N times T. Okay. As it turns out, as n goes to infinity, this formula turns into this because the more times you're compounded per year, if you're compounding continuously, that's like infinitely many times. So as n goes to infinity, this formula becomes that formula. So that's interesting, but again, we don't really care about that for this problem. So P is the initial amount, which is again still 25,000. Okay. R is a different rate. In decimal, it's 0.1026. Okay. N is the amount of times compounded per year. It's compounded monthly, which is 12 times per year. And T is the same amount of years that pass, which are 20. So I'm going to plug these in and see what I get. And I'm just going to do this in my calculator off screen. But if you want to like actually write them plugged in, I mean, you can definitely do that. There's no real benefit of me showing you that. I think the biggest benefit would be to see how to plug it into the calculator. But just try to plug it in as you think and see if you get the same values I do, and if not, you're doing something wrong. But the biggest part people get confused on with the calculator input is parentheses, of course, but more than that, n times t is in its own parentheses. So nt is going to be 12 times 10. So when you do it in your calculator, it's going to be 25,000 times whatever this is, and you can type it out, 1 plus 0.1026 over 12. And then 2, though, when you type in 12 times 20, let me just show this over here, you should have that 12 times 20 in its own set of parentheses. Because as is, it takes this thing to the 12th, then multiplies it by this, and then also multiplies it by 20. But like this, it multiplies 12 to 20 in the exponent. So that, I think, is a important piece to mention. And same thing here. When you write e to something, you want to put that something in parentheses as well. Now usually the button for E on calculators already gives you parentheses. And if you don't know where this is already, E is second ln or shift ln depending on your calculator, but usually it's that. And in fact, yeah, this one, right? So it's right here. It's a second ln. And right away when you press second ln, just to show you what it gives, there we go, we see e to the, with parentheses, just like I said. So I'm going to go off screen, like I said, approximate these, and then we'll make some conclusions, okay? Okay, here are the values I got, and yeah, like I had the hunch, I was correct. Since Bill had a bigger interest, that I kind of overtook, actually, Desmond's advantage that he was being compounded continuously. So in fact, after 20 years, Bill will have $192,896.39, where Desmond has $167,147.36. And so Bill wins. Bill has more money. So Bill has more. And how much more does he have? Bill has whatever the difference is. So I just subtracted these two, and I got $25,749.03. Okay. So 25,739. 25,749. And 3 cents more than the other guy, more than Desmond. Perfect. So that tells us who has more and by how much. Fantastic. So now moving on to number 9. All right, so number 9 here is asking us to solve these equations, and now we're kind of back to non-exponential type of questions. So it's not necessarily, the exam review here is not necessarily in order by chapter, it seems, but these aren't too bad. At least A isn't too bad. B will take a little bit of explaining, but A is actually pretty straightforward. So I want to get x by itself, so I'm going to get the term involving x by itself first by subtracting 4 to the other side. I think that should be a pretty obvious step, but let's see. So we get 2x to the 2/3 is equal to 12 minus 4 is 8, and then dividing by 2 will give you this power of x by itself. So we get x to the 2/3 power is equal to 4. Perfect. Now what do we do? Well, I mean, there's a few interpretations on what x to the 2/3 really means. So we can actually take the reciprocal power of both sides, and that really is what you should do. But just kind of keep in mind that when you're taking something to a power that has an even denominator, because the reciprocal of 2/3 is 3/2, you're really taking square roots. Or, well, if it's an even power, it's really an even index radical. And those will always give you plus or minuses when you introduce those to an equation, like we're going to. So what I'm basically saying is we'll have a plus or minus situation. So I'm just going to do that. I'm just going to take both sides to the 3/3 power. Now, remember, when we do this, we get a plus or minus. So I should write plus or minus. I don't really have space, so I'm just going to put an arrow with a plus or minus like that. Now, why is there a plus or minus? Because of the 2 in the denominator. Because dividing by 2 in your exponent is the square root, and dividing by any even number is an even index radical, which will also have this plus or minus situation. And that's, of course, because taking any positive or negative number to an even power will just get rid of the sign anyways. So it makes sense that x could be positive or negative because its power is even. So, okay. So here these cancel out completely in the power, so we just get x plus or minus 4 to the 3/2. Okay, what is 4 to the 3/2? Well, I just said that if your exponent has a denominator of 2, that's really a square root. So you can think of this actually as the square root of 4 to the 3rd, or you can think of it as the square root of 4 to the 3rd like this. Now they actually both give you the same thing, but I prefer to square root first, in fact any radical first before powers. So this way we see the square root of 4 is 2, and 2 to the 3rd is 8, so the answer is plus or minus 8 for x. And you can check it when you take 8 to the 2/3 power, you will get 4, and 4 times 2 is 8, and 8 plus 4 is 12, so it checks out. And negative 8 to the 2/3 is still positive 4. That's kind of interesting. So both of these work. Now, if you did it this other way, so maybe I should have written or, but they're the same thing. Here we get plus or minus the square root of 64, which is also 8, notice. So it's kind of interesting that we can see it both ways, but I prefer radical first, then power. Just get smaller, then get larger. Don't get larger, then it's harder to take the square root possibly. Okay, now moving on to this one. Now, when you have an equation involving denominators that are expressions, it's best to factor look for any common factors, and then multiply by the LCD, which is grouping all of the factors, including common ones. So let's take a look at that. So here we can pull out an x. Let me do this in blue. Pull out an x here. We have x minus 4. This is the difference of squares, x minus 4 times x plus 4. And let me replace these with these. And what I'm going to notice is that they have an x minus 4 in common. So the LCD in this case is actually just going to be x times that one x minus 4 times an x plus 4. Really what I'm saying is if I multiply this top and bottom by x plus 4, the common denominator will be this times x plus 4. And then if I multiply this top and bottom by x, then its common denominator will be x times x minus 4 times x plus 4. So it'll be the same thing. So this needs an x that this has that this doesn't, and this needs an x plus 4 that this doesn't have that that denominator does have. So that's a way of thinking of that. Now what's nice about this is if we multiply everything in this equation, each term, by this, notice anything times 0 is 0, so that doesn't matter. So we're going to get 0 on that side. But when you multiply these two terms, this guy and this guy, by the LCD, you get cancellation. And you can just kind of see it. It's hard for me to write it out because it'll just be long and it's a lot of writing. But if you just imagine multiplying this by the LCD, the x and x minus 4 match, so those cancel. So the top two is only really multiplied by what didn't cancel, which is 2 times x plus 4. Very similarly, this 3, so plus 3 times what? Well, the only thing that match here are the x minus 4 and x plus 4, so what doesn't cancel when you multiply this term by this whole expression is just x. So that's just 3x. So let me scoot that equals 0 in. And now this is a very simple equation to solve now. Now we just need to keep in mind that the denominator of the original expression could be 0 when x is either 0, 4, or negative 4 when setting those equal to 0. So because of this, x cannot be equal to 0, 4, or negative 4. Now the reason why I'm mentioning this is because if we get one of those as a solution in this equation as we have it here, it doesn't look like we will actually, but if we do, then it would be extraneous. It's an extraneous solution because it wouldn't check out. Plugging it back in would give you a 0 denominator. It's also possible that the equation this turns into, instead of being linear like this, will be quadratic, so you'll have two solutions. And one may be extraneous, in which case you ignore that one and your only real solution is the one that's not extraneous. But in this case, we don't have any of those strange scenarios. You just get 2x plus 8 plus 3x. The x is combined to 5x. We can subtract this 8 to the other side. So we get 5x is equal to negative 8. Like that. And then dividing by 5 finally gives us our answer that x is equal to negative 8/5. Which is not extraneous because it is none of the values that would have given us a denominator of 0. So you can actually check it if you wanted to. I'm not going to, because it's a lot of work and I have to like check and go back and forth. But try it on your own. I encourage anyone to try. This I kind of checked. This one, not so much. But you should check plugging in negative 8 over 5 to this denominator and to this denominator will end up giving you the same fractions, but opposite so that they combine to 0 indeed. Great. So that was nice. Now let's move on to number 10. All right, so now number 10 here asks, do the following functions have inverse functions? And if so, let's find the function. Find the inverse function. Now, only one-to-one functions have inverses. So if we graph these and we see that it fails the horizontal line test, it will not have an inverse function. That's an easy way to see that. An easy way to see that that's true is that if you have any function, f, then its inverse function, f inverse, is going to have a graph that is basically swapping the x and y values. So usually the way you see that is actually you graph the line y equals x, which is this diagonal, and you reflect this about that. So I'm not going to do it complete justice, but it will look something like this. Okay? So just reflecting this about that line will give you the inverse function image. And it is an inverse function if it passes the vertical line test. And of course, it'll only pass the vertical line test if before this flipping, it would pass the horizontal line test. So functions that pass the horizontal line test are called one-to-one functions. And in fact, we saw this one-to-one property when we solved these exponential equations. And the one-to-one property is true because exponential functions, provided the base is not 1 and positive, are one-to-one functions. And what are the inverses of exponentials? They're actually logarithms. So that's nice. We don't see that here, but it's just a nice kind of lecture point. Okay, so if I were to graph this, notice this is actually a transformation of 1 over x. So its graph is going to look very similar to 1 over x. And 1 over x will have a graph that looks something like this. Since this x is replaced with x minus 3, then everything is actually shifted over 3 units. And in fact, it makes sense because the vertical asymptote would be when the denominator is 0, which is at x equals 3. So the graph of this is actually going to have a vertical asymptote at x equals 3. Let's just do that, I guess. And you'll have something like this happening. Now the 2 on top means it's stretched out by a factor of 2 vertically, but that doesn't really affect it passing the horizontal line test. It still passes the horizontal line test. It may look iffy here, but remember there's a horizontal asymptote at the x-axis, so it will never touch that horizontal line. So these never cross or anything. Okay, so this is one-to-one, so this actually does have an inverse function. So does it have an inverse function? Yes, it has an inverse function. So I guess that's our first answer. But now what? Well, now let's find it. How do we find an inverse function? So this is interesting because if you wanted to, you can just jump into the process of finding the inverse function, and if you get something that's not a function, then that tells you that the answer was no, actually. But graphing, if you can, and seeing that it's one-to-one, is I think probably an easier thing to do just to get a quick yes or no. So in fact, looking at this, what do you think? Is this one-to-one or is it not? Well, it's a quadratic, which have graphs that are parabolas. And in fact, this is just a transformation of y equals x squared, just again stretched out vertically by 2, coincidentally, the same 2. And this for sure fails the horizontal line test basically everywhere. So this is not one-to-one. So again, the fact that this was one-to-one told us that yes, this is a function that has an inverse. But here this is not one-to-one. So this unfortunately does not have an inverse. So the answer here is no. I don't know why I'm putting exclamation points, but you get the idea. Okay, but now what? Now how do we actually find, so I've answered the first question for both of them simultaneously. But now how do we actually find the inverses? And again, you can just jump into the process and that'll actually tell you if it was actually true or not. And you'll see what I mean in a moment. So I'm going to erase some of this stuff here. And let's see. I guess I'll erase this. So the process to, let me border this off a bit. The process to find an inverse function is basically to swap x's and y's, because we saw that in the graphs. If you swap the x and y values, then you get the you actually get the inverse, the graph of the inverse function. And if you swap x and y values here, you'll also get you'll get the inverse function. But of course, we let f of x be equal to y. So I'm going to swap x's and y's and attempt to solve for y. So the first step in doing this is to swap x's and y's, and we get this. The second step is to actually solve for y, and then we can replace that with f inverse now. So when y is equal to something in terms of x, that y we can replace with the f inverse function notation. So this is pretty simple to solve for y. Multiply both sides by y minus 3, and you can also divide by x simultaneously, but I'll just do it one step at a time here. Multiply both sides by y minus 3. Notice y minus 3 will cancel on that side. Then divide both sides by x. So we get y minus 3 is equal to 2 over x, and then add 3 to the other side, we get y is equal to 3 plus 2 over x. Perfect. Now the final step, I think, would be to just use that function notation. So here I'm actually doing this process. Replacing f of x with y, then swapping x's and y's for the first step, solving for y, and then finally replacing y with the inverse function notation. And if you want to combine these into one, you actually can do that. It's not too hard. Notice 3 is 3 over 1, which is 3x over x. So they actually combine to 3x plus 2 all over x if you wanted to write it as one fraction. But this is fine too. And you can verify by graphing both of these that you'll see that they actually are flipped images about the line y equals x. So that's kind of nice to see that. Also, just to kind of give an understanding of what it means to be an inverse function, is it undoes what the function does. So if you pick a random number that's in the domain of f, so not 3, let's say 5, let's plug it into f and see what we get. Plug 5 into f, you have 2 over 5 minus 3, 5 minus 3 is 2, 2 over 2 is 1. So if we found the correct inverse function, I picked 5 randomly, you plug the output of f into the inverse function, and that'll undo what f did. So it should give us 5, let's see. Plug in 1 into the f inverse, 2 over 1 is 2, 2 plus 3 is 5. Nice, it works. Now this is not a very general thing to do, but provided you're picking your input randomly, it's a nice check to understand what's going on. If you want to actually check for all x values, you would compose this one with that one or vice versa, and see that things cancel out and you just get x back. But you get the idea. Now b we don't need to do because we already found it, but we already found that it was no, and we only need to find the inverse function if one existed, of course. But I still want to go through this process and show what happens if you just tried. It's kind of interesting. So if we replace f of x with y, we get y is equal to 2x squared. And then if we try to solve for, well, I should say we swap those, sorry. We swap x's and y's after replacing f of x with y. So it's this actually. Okay, great. So now to solve for y, divide by 2. X over 2 is equal to y squared. And then to get y by itself, when you square root both sides, you get plus or minus the square root of x over 2. So this is an inverse relation, but it's not an inverse function. Why is that? It's because of the plus or minus. In fact, the plus or minus indicates that there's 2 different y values for any x value you give. And that is not a function. A function will have only one y value for any x value. So you plug in an x value, you know what the answer is. But here you plug in an x value and you get 2 answers. It's kind of a weird machine, I guess, we're building. Anyways, it's kind of interesting to see though. If you were to graph this, the positive square root will give you a kind of square root graph like this. So that's the positive one. So this is y equals positive radical x over 2, something like that. And the negative one I'll draw in blue below. This will be y is equal to negative radical x over 2. And notice together this fails the vertical line test, so it is not a function. One of them at a time is. So if we had some restriction on x, like x must be positive, then that means that when you take square roots, you'll get the positive root. So there it would have an inverse actually. But there's no restriction here. And in fact, what's interesting is that even if you were to just grab this whole image and reflect it about that vertical line, not vertical line, about that diagonal line, there we go, you'd still get this. So that reflecting is actually independent of if it's a function or not. But it being a function, we can kind of tell ahead of time by pre-screening with the horizontal line test. So that was kind of nice to see that. And again, because it's not a function, that means the inverse function doesn't exist because it's technically not a function. So the answer would have been no. So it's nice to see that. So that was it for the review. I hope you all enjoyed this and I wish you luck on the exam.